Christine Williamson.
Hey everyone, thank you, Anna. Thank you, Huber, for hosting. I'm so glad to be here, actually, talking about something new. I have not taught on acoustics before, and I'm so glad to be doing it. My name is Christine Williamson. I'm a building scientist, and my background is in architecture. I actually started my career in New York City working for a fantastic architect there, Chris Benedict. And during my time in the city, as you might imagine, I met a lot of very interesting characters, including a particularly clever real estate investor and developer. And over decades of building, operating, and maintaining multifamily buildings, this developer had discovered a peculiar little trick for assessing how much trouble and expense an existing building would be to operate should he actually go and acquire it. So he would ask to see the pest extermination bills, not the architectural drawings, not the utility bills, not the energy certification, but the extermination bills. And what's interesting is that pervasive pest problems, as he discovered, also generally mean energy inefficiency, odor problems, acoustic problems, all problems that are difficult and very costly to address once a building is occupied and a real pain to maintain. I think there's a lesson here for those of us who are involved in new construction. And that is that an individual design mistake or installation error can produce multiple and compounding problems, right? It's not just acoustic problems, but pest problems, energy problems, odor problems. And that's not fun. That's not good. Compounding problems are obviously really problematic. But it's also true that a single wise decision, well executed, can lead to disproportionate benefits in performance. And this is very true with respect to acoustic performance, as we're going to see. Acoustic comfort is really closely related to other very desirable things like indoor air quality, pest control, energy efficiency, odor control, and even thermal comfort and fire protection. So this presentation is focused on lightweight construction, so wood-framed multifamily buildings. And when we talk about performance in these types of buildings, multifamily buildings, what we're really concerned with is noise control. Oh, and I'm a bad CE provider here. Here's the course description, learning objectives. I hope you, I wrote a really nice course description. I hope you take a look at it. It was pretty, I'm proud of that one. Anyway, what kinds of noises bother people the most? In fact, we know the answer to this. Sounds that are created by sources the listeners are not involved with, sounds that are unpredictable, sounds that are perceived as unnecessary, and sounds that are generated, this is my favorite, sounds that are generated by people the listeners don't like. So as you can see, the very premise of multifamily construction invites exactly these kinds of irritations. What I think is really interesting here is that there's a psychology at play, right? And a valid and successful acoustic strategy would be for building management to have a good relationship with tenants and for management to foster, encourage good relationships among neighboring tenants. What's even more interesting about that is that not only makes it less likely that a tenant will complain, it makes it less likely that a tenant will become annoyed in the first place, which is crazy. Now, of course, this is not something that architects have control over. Our strategies for dealing with noise control are going to have to be limited to things that are related to design and construction. But this is, I think, very interesting to acknowledge nonetheless. In multifamily design, we are primarily concerned with sound isolation. And to that end, it's helpful to distinguish between airborne sound and impact noise. Airborne sound is fairly intuitive. It's sound that travels through the air. Impact noises are radiated to the structure through furniture movement, through dropped items, rolling carts, normal use activities like using the kitchen, exercising, cleaning, slamming doors, whatever. But in almost all cases, when we're dealing with acoustic problems from impact noise, we're dealing with footfall, people walking around. When feet strike a floor, they set that structure into vibration, and those structure-borne vibrations can travel actually very far. The types of floor ceiling assemblies that do well in keeping airborne noise out of the room below are not necessarily effective at keeping structure-borne impact noise from radiating downward. And the reverse is also true. Assemblies that are good at mitigating impact noise are not necessarily also good at mitigating airborne sound. So it's really important that we consider these things independently. With airborne sound, we are concerned with all 6 sides of an individual unit. So we care about the exterior wall, party wall, corridor wall, and the floor ceiling assembly. But with impact noises, we're primarily concerned with that floor ceiling assembly. Because again, it's the footfall that tends to be the most irritating. So we've got airborne sound and we've got impact noise. We get complaints related to both in multifamily construction, but these 2 types of sound call for very different responses from designers who are seeking to minimize acoustic problems. With respect to airborne sound, the most reasonable way of reducing complaints and increasing performance is usually to ensure that the existing standard acoustic details that we've got in our drawings actually end up being implemented on our jobs. So in other words, we tend not to have a design problem. We have an installation problem most of the times with respect to airborne sound. Now, impact noises are completely different. Improving performance related to structure-borne sound usually requires design changes to that floor ceiling assembly. And when we do this, sometimes we're completely redesigning the whole assembly, right? But most of the time, the most reasonable approach is for us to substitute existing materials with higher performing alternatives, usually in the form of higher performing flooring finishes or underlayments. Before we move on, I want to mention that a lot of information on acoustics is pretty academic and it's fascinating. A lot of the academic stuff comes from a book by Michael Ehrmann. I'm not sure if I'm pronouncing his last name correctly, E-R-M-A-N-N. I've cited at the end. Fantastic textbook. He's a professor at the University of Architecture at the University of Virginia, or UVA. Is that how you, well, anyway. Anyway, great book if you're interested in more of the academic stuff, which we're just going to touch on lightly here. But practically speaking, a lot of that stuff, the academic portion, is really not sufficient for achieving success in real buildings. We need to know not just how to maximize performance, but how to do so while working within the typical constraints of multifamily construction. So completely redesigning our assemblies is usually not a realistic option for us. So we're going to talk a little bit about the higher level academic stuff, but mostly what we're focused on here today are those realistic options for improving acoustic performance in real projects within typical practical constraints. So let's start with airborne sound. It is super helpful to talk about the concept of transmission loss. So transmission loss quantifies the airborne sound insulating properties of a building element. So it's a lot like R value, actually. The higher the TL value, the more robust the assembly is at attenuating sound. What's interesting here is that building elements and assemblies will have different transmission loss numbers depending on what frequency they are tested at. So this is actually a lot like R value. The insulating value of a material, the thermal insulating value of a material, actually changes depending on the temperature on either side of the material. So we'll get insulations that perform worse or better depending on how we run the test. Are we testing the insulation assuming an exterior temperature of 70 degrees Fahrenheit, or 40 degrees, or negative 40 degrees? We get different answers. Now, this usually doesn't matter for us for practical purposes for thermal insulation, although sometimes it does. With respect to sound, we see something similar. Transmission loss information for a material or an assembly will not be a single value, but a collection of values from different octave bands across the frequency spectrum. So sound transmission class, or STC, provides us with a single number rating for the transmission of airborne sound through an assembly. And this one is more akin to R value in that even though we know the R value changes for insulations, we just use the single value as a general rule of thumb. So STC is like that. Transmission loss values give us a more complete picture, but STC gives us a single simplified metric for assessing performance and comparing different assemblies. The higher the STC rating, the more effective an assembly is at mitigating sound transmission through it. STC is measured, it is not calculated, and its unit is decibels, which is a measure of sound volume. The STC rating roughly equals the decibel reduction in noise that a partition can provide. So for example, if an 80 decibel sound on one side is reduced to 50 decibels on the other side, the partition would have an STC of the difference between the two around 30. Now, that's not exactly true, right? Remember, STC is measured, not calculated, and it's based on sound taken at a bunch of different frequencies that are then combined into a magic formula to yield a single number. But that is the general logic. The STC scale is a logarithmic scale that's going to matter to us. So it's not linear. A 40 decibel noise subjectively seems half as loud as a 50 decibel noise. We'll talk about more of that later. Before moving on, STC is particularly good as an indicator of noise isolation for speech, but the single value simplicity of STC comes at a cost. So it's a pretty good indicator of acoustic control related to speech, but it's typically not great as an indicator of how an assembly will perform with respect to low frequency sounds. So in some cases, STC ratings really aren't very good at comparing assemblies when the sounds in question are particularly low frequency. It's a lot of music, right? Let's look at an example of that. Suppose we've got a simple uninsulated stud wall. These are walls shown in plan. I'm showing two walls in plan. And the first one, simple uninsulated stud wall with a single layer of gypsum board on each side. This wall will have an STC rating of about 34, but the transmission loss values you can see here, I think you guys can see my mouse, vary quite a bit, right? Between 15 and 41, depending on the frequency. So 15 at 125 hertz, 41 at 4,000 on the high frequency side. If we switch to a double stud cavity insulated wall with two layers of gypsum on each side, we might have an STC of 62, but transmission loss values vary between 44 now and 65. And in both of these cases, both of these walls, STC, you can see, is more representative of performance at the mid and high frequency ranges, really not very predictive of performance at lower frequencies. Just something to keep in mind. So what can we do to mitigate airborne sound? We can add mass, we can add an airspace, we can add absorption to the airspace, we can provide structural discontinuity, and we can air seal. We're going to talk about each of these briefly because the principles that inform the design matter and are helpful in how we actually go about our work. But again, realistically, we often don't have much choice here in a lot of our projects. We can't just infinitely add mass to lightweight construction. We need it to still be lightweight construction. We're not going to buy the kind of resilient channels that they use in professional sound studios for every mid-rise apartment building. Important to note here before we move on is that of these design factors, air sealing tends to be the least competently implemented. And as we'll see, that is really the low-hanging fruit in terms of improving performance with respect to airborne sound. So what can we do to improve STC performance with respect to airborne sound? We can add mass. 2 layers of gypsum board performs better than a single layer. We can add an airspace. 2 surfaces separated by an airspace perform better than a single surface. We can add absorption to the airspace that will further improve performance. This is in the form of insulation usually. We can provide structural discontinuity, and that helps as well. We can do this by staggering the studs. It's a typical stud wall, staggered studs. Or by building a double stud wall up here, or by using resilient channels. So that's this is in plan, so you can't really see the resilient channel, but it's offset there. But what I really want to focus on here is air sealing. There is a lot of acoustic awesomeness going on in this photo. This is a party wall between 2 dwelling units in a multifamily apartment. And I'd like to call your attention to the drywall extending all the way up to the subfloor above. Notice that it is notched around the floor joists. And notice that sealant seals the drywall to the joists and to the underside of the subfloor above. We know there's going to be a suspended ceiling here, and we can see the resilient channels for that. We can see that those channels don't actually touch the wall. We can see that the penetration in the photo is sealed with fire caulking. Speaking of which, you are supposed to do all of this air sealing anyway to meet fire code requirements. But hear me when I tell you, this is often not done. Job sites are really busy and inspectors can only see so much. When architects walk a job, they can be reluctant to bring this up because nobody wants to be critical of work in progress, right? And when the ceiling is in, of course, we don't know how well or even if this was done at all. It's very, very common to miss this, sometimes egregiously. So let's talk about STC ratings in context. If you are separated by a partition with an STC rating of 30, normal speech will be audible and might even be intelligible. At 40 STC, loud speech will be audible but not intelligible. At 45 STC, loud speech will be barely audible. And at 50, shouting will be barely audible. 55, shouting will generally not be audible. And at STC 60, you might be able to hear music. The code requires separations between dwelling units to be rated at 50, STC 50. But remember that this is a measured rating and it's measured in a lab. So just because you design STC 50 doesn't mean that that's what you'll actually get. Now, a note again about STC differences and perception of loudness. This helps put things in context for us. If we improve or reduce an assembly's performance by 1 to 3 decibels, a person might be able to notice it, but probably just barely. A 4 to 6 decibel change in performance will be clearly noticeable, and a 10 decibel change will be dramatic. Remember here that we're using a logarithmic scale, and a 10 decibel change will either double or halve the perceived sound. A helpful concept for us to consider when we talk about actual performance versus design performance is that of flanking. Noise control is a lot like water control in that its success is heavily influenced by performance at the weakest part of the assembly, not the average performance overall. So 90% success is basically a total failure. Flanking is the term we use to describe acoustical pathways that bypass our sound mitigation efforts. So they're akin to leaks, basically. These pathways end up being so influential that a 1/16 inch crack, 16 inches long, will reduce an STC wall to an STC 50 wall to an STC 40 level. And remember what a 10 decibel change means for us. It means that our tiny 1/16 inch crack has just cut performance in half. So it's taken us from shouting is barely audible to now we can even hear loud speech. So that's really not good. Now, if we want to present this graphically, I think it's helpful to see. This is a graph showing how different walls perform acoustically based on different flanking conditions. So all of the walls plotted here are double stud walls with 2 layers of gypsum on each side. The most poorly detailed installations with the most flanking down here performed substantially worse than the average walls and the best walls. And this is true at all frequencies. So we're looking at a difference of about 20 decibels, and that's fairly consistent across the frequency range. This is for the same design. This is the same design. So flanking in this situation is very influential, and it's almost entirely related to air sealing. So what this tells us is that improving airborne acoustic performance in multifamily construction is mostly about field verification of air sealing details, not more expensive design. Field verification, this is an installation issue. So what are our particular weak spots in this regard? Typical, they're exactly what you might imagine intuitively. The wall-to-ceiling interface, the floor-to-wall interface, back-to-back penetrations in party walls, penetrations in the same stud bay in party walls, windows and doors themselves, and then the window-to-wall or the door-to-wall connection, and then penetrations. So how can we actually get the performance we specify? We can provide enlarged details in our drawings, specifically for acoustic performance. And each one of the line items from the previous slide should be detailed, and we should verify the installation in the field. This is my totally awesome party wall again. Beautiful. But this is the kind of stuff that we routinely see. This is a plumbing penetration that's, first of all, much too big. Looks like they used a chipping hammer or something to make this hole, and they made it substantially larger than it needed to be for the penetration to fit. And the larger you make the hole, the less likely it is for fire stopping to be installed properly. Here you can see that someone sort of made an effort to stuff some mineral wool in there at some point, but it's not exactly doing much. And it did not have to be this way. A core drill rather than a chipping hammer would have allowed us to make a much smaller penetration that would have been more reasonable to air seal. And these are penetrations through concrete slabs. So it's not quite our situation in lightweight construction. So the means and methods are a little bit different than wood construction, but the concept is exactly the same. We have lasers and we have core drills, and there's no reason that this can't be laid out more attentively to facilitate the air sealing. This is a way that trades can show respect to the trades that come after. A lot of architects are really reluctant to bring this stuff up because designers often don't have a very good handle on how hard whatever it is they're asking for is. And it's also work in progress, and no one likes to be criticized for work that isn't finished. But I am here to tell you that your intuition is probably right about this stuff. If it doesn't look easy to air seal, it won't be easy to air seal, and this matters a lot. Not only does it matter from an acoustic perspective, but it matters from a pest control perspective, and all the other things that we talked about earlier. This is a fire hazard. It's awful for acoustics. It's awful for energy efficiency, for pest control, for odor control, for indoor air quality. And it doesn't have to be this way. But it frequently is. This is another unsealed plumbing penetration. These photos are from retrofits. We open up buildings in the process of redoing them and find that they were never done properly to begin with, and sometimes in very egregious ways. Another one, just not sealed. Plumbing penetrations that were not sealed. This is a party wall meeting a ceiling. You can see how the gypsum at the wall here was removed as part of the retrofit, and we can now see that there was no fire stopping installed at the perimeter. This is really bad, and unfortunately it is very, very common. This is not an air sealing example, but it is an example of verifying performance in the field. Pull the specifications on whatever resilient channels you're using, and make sure the correct fasteners are used in the appropriate way. Fasteners should not penetrate both of the components that they're meant to offset, obviously. The next image I'm going to show you, so these things properly are offset. Unfortunately, sometimes we see this. This image is provided by the manufacturer. I'm not going to say which, but they're showing an example of exactly what we want to avoid. They've got a fastener going all the way through their channel to the stud. Not setting a very good example. Other common flanking issues are electrical boxes. So ideally, you'd not have any at all in a party wall, but if it's necessary, you'll at least want them in different stud bays. But this is what is more typical. This is not great. And we've got a sort of half-hearted attempt at air sealing, but those metal boxes in particular are just terrible for sound transmission. This is much better. We've got the electrical boxes in different stud bays, and each one is air sealed with putty. This is a closer view of that. These are called putty pads. You can also buy proprietary electrical boxes that make air sealing quite a bit easier, and they improve acoustic performance. This one is made by a company called Airfoil, and it's got kind of an outer chamber that gets filled with open cell spray foam to achieve the air seal. You can see some of the spray foam sort of smooshing out of the top there. Whatever you end up doing to air seal behind the box, you'll also want to seal the box itself to the drywall. This is obviously work in progress. You're going to want to tool that sealant, but it needs to be sealed. As for windows, these matter obviously for mitigating street noise, for sound transmission through that exterior wall. What I'd like to highlight here briefly is the interior air seal. So this one. This sealant joint should be a full perimeter seal, and it should be installed by the glazing contractor, not the drywall installer or the painter. This is not a finish seal, it is a performance seal. And one of its purposes is acoustic control. I see this interior seal missed a lot on architectural drawings, which makes it less likely that it will get bought and installed by somebody. The architect will show an interior seal. They'll show this one, but it'll be that finished seal between the drywall and the window frame, or the trim and the window frame. And that's not sufficient. You want to make sure that both seals are included, both the finished seal and the air seal. This is what that looks like, that interior seal looks like. Notice that we can see it before any interior finishes are installed. We seal that joint between the window frame to the membrane sill flashing that's been turned in at the rough opening. If two spaces share air, they share a common acoustic environment. And what we're really driving at here is compartmentalizing each unit in a multifamily building. And the best way to verify performance, apart from looking at these details during design and construction, is to perform blower door testing. This is actually not all that expensive. We specify window testing all the time, where we do water leakage testing on a handful of windows. You can require that all units be tested, or only certain ones. This photo is of me. This was my first job in architecture, and it was my job to test every unit in the apartments that we designed. The test works by using a large fan to pressurize a unit, a space, to a set pressure, and then we can infer how many times all the air in the unit would be replaced if we were to run the test for an hour. So we measure it in air changes per hour, or ACH. And we'll report the results as air changes at whatever pressure we tested at, which is usually 50 pascals. What's neat is that while you're running the test, you can, if you're inside, you can walk around the unit and actually feel the air, feel with your hands, feel the air rushing through anything that was left unsealed. So you know what needs to be repaired. To put this in perspective for you, we know that very attentive design, in which we detail the interior drywall to be the air barrier for each unit, can achieve 0.6 air changes at 50 pascals, which that reaches Passive House standards, and it's awesome. That is a really high-performing apartment. It's very comfortable. In retrofit settings, we're looking at about 3 to 4 air changes, depending on how much work we're really doing. I'm assuming we're down to the studs. Maybe we're also replacing the windows. But perhaps the most interesting data point I'd like you to really remember is what apartments tend to test at prior to being retrofitted. In my experience, that's as much as 14 or more air changes. It is crazy how bad a lot of these apartments are. And it's not the detailing, typically, it's the installation. Now, that is obviously not good for a lot of tenants. A lot of people are really needlessly uncomfortable. And it goes a long way toward explaining a lot of problems in multifamily construction, the pest problems, thermal control, energy problems, kind of stuff, fire safety problems. But this also represents a really big opportunity. Things are really bad out there, so if we make them better, it's not that hard. We know what to do. We're not confused by it. So ask for more from your contractors, and really don't be shy about it. That's what they should be doing anyway. So with airborne sound, I think I've made a pretty convincing case, I hope, that our issue is really with the implementation of stuff we already know is a good idea. But impact noise is is going to require something different from us. To improve performance with structure-borne sound, our most reasonable strategies are design strategies. So we want to make design changes to existing assemblies that improve performance. Structure-borne sound or impact noise has its own metric for acoustic performance. Rather than STC, we're concerned with IIC or impact insulation class. Sometimes it's called impact isolation class, same thing, but it's still IIC. This is a single number rating like STC that allows us to compare different floor ceiling assemblies for the transmission of impact noise. The higher the IIC class, the better the assembly performs. So like we did for STC, let's put those IIC numbers in context. A floor ceiling assembly with no acoustic consideration might earn an IIC of about 30, which most occupants would find to be unacceptable. On the other end, an assembly specifically designed for acoustic control might achieve an IIC of 70, which most occupants would find acceptable. And then code is in the middle. The IBC requires an IIC of 50 for floor ceiling assemblies. And what we find, though, is that some occupants find that acceptable and others really do not. And this is both a problem and an opportunity for us. So we find that minimum code performance is really not aligned with widespread occupant satisfaction. And that means that this is an area in which it's really beneficial to exceed code minimum. So how can we control impact noise? We can position noisy areas far away from quiet areas. Maybe we can avoid stacking units altogether, like in a townhome configuration. But a lot of times we're just really limited with that too. It doesn't make financial sense to organize plans any other way. We can provide damping at the point of impact. So basically we stop the sound energy from getting into the structure in the first place. The easiest way to do that is with flooring finishes like carpet, or we could specify something like cork or rubber. Now, obviously, these aren't always suitable for multifamily design. We have other constraints that we're dealing with. We can provide damping within the floor ceiling assembly. We could provide some kind of underlayment under a hard flooring finish. These are usually proprietary systems sold with the flooring and installed by the same subcontractor. Usually with these underlayments, the thicker the better. We can and usually also do provide dropped ceilings in multifamily construction, and that provides some damping as well, especially if we install the drop ceiling on resilient channels or some kind of support system that decouples it from the structural floor above. And finally, we can provide additional stiffness and mass. So we can provide denser spacing between the joists or trusses. 24-inch on-center spacing is very common, but depending on the particulars of any given project, it may actually not be difficult or hugely difficult or costly to take that down to 16 inches on center. Trusses are not super expensive, so that's something to keep in your back pocket. But even this is tricky. To really maximize acoustic performance, we'd want the deflection of the floor to not exceed 1/8 of an inch under a uniform dead load of 40 PSF. That is, put that in perspective, about 1/4 of the conventional deflection limitations, and that really may not be realistic. Another way of adding both stiffness and mass is to add an underlayment over the subfloor. So this is why gypsum concrete is commonly included in multifamily construction. It increases acoustic performance by doing exactly this. So gypsum concrete is installed wet. It's poured over the subfloor, and it increases the IIC performance. But you could also add something better than gypsum concrete. Just like there are different floor finish underlayments that provide different levels of acoustic performance, there are also performance differences in the underlayment materials that get installed over the subfloor. And gypsum concrete is not the only option. Magnesium oxide boards tend to perform better than gypsum concrete. They are rigid boards that are mechanically fastened in to the subfloor by the framing contractor. So how much better do they perform? A lot better. So if we consider the same sort of base assembly, we've got from bottom to top, drop ceiling insulation, open web trusses, a standard subfloor, and either wet laid gypsum or magnesium oxide. This data is from Huber's Exacor product. We see substantial improvements in performance, and we see those improvements in performance in exactly the place we want to see them, which is the IIC and a different value I haven't spoken about yet, the HIIC, which is a measure of, it's still IIC, but it's of high frequency impact noise, and that's a metric that tends to be more predictive of occupant satisfaction in multifamily construction. So it tends to be an even better indicator than IIC. Our industry is moving that way. And what do we see? So we've got, these are the STC, IIC, and HIIC numbers for either gypsum here or for magnesium oxide boards, Exacor. And I've highlighted the difference in performance. The light shading is areas where we see a noticeable improvement, and then the darker shading is areas where we see dramatic improvement. So, and those are very dramatic. And remember, this is in an area where people tend to really not be satisfied by the baseline level, so the code required minimum. So anything we can do should greatly improve performance and reduce complaints. Now, there's some genuinely useful, actually, I'm gonna go back to this because I don't want you to read all this yet. There's some genuinely useful information that I really wanna talk about discuss with you, but I think it will benefit us for me to be really forthright with my approach. This session is sponsored by Huber, and I am delighted that Huber supports professional education, but I am not a spokesperson, and it is not my job to sell you Exacor. I'm a building scientist and I'm a teacher, and what I'd like to do now, though, is use this proposed design change, so replacing gypsum concrete with magnesium oxide board, as a way of talking about some construction concepts that are very, very helpful, not just in discussing acoustic performance of floor assemblies, but that are helpful concepts for evaluating all details and assemblies. And I hope that this will lead into a good question and answer session. So I want to actually talk this through. Suppose you're an architect and you're considering using Exacor because it performs substantially better in service for these reasons right here. Or it gives you more freedom in selecting a floor finish. So you meet your acoustic rating with the underlayment, and now you have a wider selection of floor finish materials to choose from. Okay, so that's the proposed change. You want to consider doing that. But that is not enough. You also want to have a thorough understanding of the consequences of making that change. Are there any trade-offs that you will need to take into account? And here is where these questions come in really handy. So how is, these first three are the big ones. How will the work be divided among the trades? How will the installation be sequenced by the general contractor? And how is this going to be bid in the first place? So these are the main questions that you will want to keep in mind with every assembly you design. These concepts are relevant to acoustic design. They're just as relevant to acoustics design as they are to how you detail your windows and your parapets. Now, I should also point out that these things are not the responsibility of the architect, but understanding these questions is enormously helpful in helping the architect to decide on a design with the greatest likelihood of successful implementation. So let's actually talk about how these things and how they relate to our floor ceiling assembly and switching from a wet laid gypsum concrete to a magnesium oxide board. So first, by using a board product that's installed early in lieu of gypsum concrete installed later, we're making a really big change. We are eliminating a trade. So the gypsum concrete is installed usually by its own trade. It gets bid separately from everything else. It's its own scope. So it's not, for example, done by the flooring installer. So this is a helpful change, right? We eliminate one trade altogether and we add that work to a trade that's already on site. There's always going to be a framer. Now, will the framer be competent enough to handle the larger scope? And are there framers willing to do this work? Those are important questions. If the answer is no, this proposed change just got a lot less appealing. But the answer in this case probably isn't no, right? Framers, we know that framers are skilled labor. And second, this new task is pretty similar to what they're already doing. So installing a board underlayment is pretty similar to installing the subfloor, which they're already doing. So we've got there's a low likelihood that we're going to have an issue there. This is a good indication that this is a reasonable change so far. But what about the willingness of the framing contractor to take on this work? Chances are probably pretty good here too. But this is not always the case, right? I have a bear of a time getting stucco contractors to install drainage mats in California. And it's not that it's particularly complicated or expensive. It's just too much of a departure from what the stucco contractor is already doing. And they have a lot of other work already, so it's easy enough for them to just walk away from the job. So that's related to the labor market. So that's just something to keep in mind. We don't design in isolation. So back to acoustics. So I lost my train of thought here. Are there other labor and sequencing consequences to this change? Do we have any other things to consider? Yes, there are. So this work gets done early. This is great in that we get to avoid multiple mobilizations or weird prep work that often accompanies gypsum concrete work under things like bathtubs and showers. Those have to be detailed first before the gypsum concrete is ready to go in everywhere else. So we've got an existing situation where we've got multiple mobilizations that are required to get the job done. And this imposes constraints when it comes to scheduling and lead times. So not having to do that simplifies coordination later. But it's always trade-offs, right? But if this stuff is in early, we need to make sure that it's able to handle exposure during construction. That's a really big deal. Your contractor will care about this. If a higher performing material had, if whatever we're considering had the composition of cement board or gypsum, we'd have a real problem. I can break cement board with my hands. So your contractor is going to want to know whether this material will stand up because it's going to be his responsibility to protect it during construction. And this is where you probably want a sample of it. You might want a mock-up. I actually, in fact, have a sample. And I took a hammer to it. That's what I wanted to know. This is crazy. I barely made a dent, by the way. I had to stop because I was scaring the dogs and probably the neighbors. But how about some other constraints? Does this change require any moisture mitigating efforts? Also a good question to ask about any design changes. The answer is no. And in fact, it gives us more freedom in that regard. So it's replacing something that's very wet. So in controlling construction moisture, our job just got easier on the whole job, not harder. What about temperature constraints and UV constraints? Those are other ones. UV is not really relevant to us here because this is going to be the roof is on. But temperature constraints, yeah, we actually get more freedom here. Wet laid gypsum needs to cure at relatively warm temperatures. That might not matter if your project is in Phoenix, so maybe you don't care. But if you're building in Chicago in the winter, this gets to be one less thing to worry about. Now, before I move on from this, I want to point out how contextual the sort of hypothetical answers we were talking through were. So projects are bid and sequenced a bit differently everywhere, and labor markets are organized differently, and climates are different. So I outlined in this sort of hypothetical line of thought that we went through together, I outlined a pretty typical scenario in this conversation, but I really want to communicate that the most useful part of what I'm proposing here is a framework for thinking about design improvements, not the specific end result. So I'm taking you through my logic so that you can adapt it as you wish for your own work, and knowing that some parts are going to be more relevant than others, some things you're going to value more than others depending on your particular case. It is very rare for a design improvement to be 100% appropriate in all scenarios. Considering the trade-offs and unintended consequences, particularly those related to adjacent systems and trades, is critical for making intelligent decisions about our materials and assemblies. This is true of acoustics, it's true of water management, it's true of energy efficiency, and pretty much everything else. A lot of times we find false efficiencies, and we want to avoid those, right? One step forward, two steps back is ultimately not very helpful. Or it might be, right? Maybe one step forward in an area that's really important to us, and we view the two steps back as being a pretty good trade. But we cannot make that decision in either direction if we're not actively thinking of the building as a system. And that's where these questions really, really help. We're not just designing it, it has to be built. And thinking about how that happens really helps us. So let's bring this all together. What can you reasonably do to improve acoustic performance in multifamily construction? The first thing we can do is air seal, provide air sealing details, inspect the work in progress, and add blower testing to the scope if you possibly can. I can't stress that enough. The blower door testing is really, really helpful. The second thing we can do, and this relates, so this first part, again, deals mostly with airborne sound. So it makes sense, right? Airborne sound, we air seal. With respect to impact and structure-borne sound, we can make design changes to the floor ceiling assembly and use higher IIC rated materials, particularly those that perform better at higher frequencies. That is just about everything. I'm posting here, I just want to show you this last slide to let you know where you can get additional information on acoustics. Architectural Acoustics Illustrated is a great textbook. This is, it's the principles of acoustic design. It's not so much a practical discussion that we covered here, but it's the foundation for everything we talked about. So a lot of the information came from that. If you're interested, I highly recommend it. And that's about it. I know that there are people at Huber here who would be absolutely delighted to talk to you more specifically about Exacor and about performance at high frequencies and all of these questions. Ask them these things. They can help you with this stuff. That's the best way to get a good understanding of this, is to ask people who are used to doing it. So there's plenty of resources to do that. So thank you so much. And I see Anna is back on. You probably have something great to say.
Yes. All right. So this does conclude the AIA presentation. So we will email out those certificates to everybody within 10 business days of the close of the event, or report directly to your AIA transcript if you provided your AIA number to us. Like I said, we will be following up with that within 10 business days after the close of the event. And so let's go ahead and turn it over to some Q&A. We got a lot of questions.
Good. Should I stop screen sharing?
You can, or you can leave it up, either one.
I'll stop. I can see, I actually can see, well, I can see some of the chat questions. I guess we're on 2 platforms, but.
Yes, we are on 2 platforms. So there's questions coming in from both directions. So I tried to compile together a little list that we can just kind of kick off with. And then if we have additional time, we'll jump into the Q&A and start answering some more of those. All right, so the number 1 question we got was, can you clarify the book you referenced by Michael Ehrman?
Oh, yes. Well, now I stopped screen sharing. But anyway, it's, actually, hold on just a sec. It is available on Amazon.com. Architectural Acoustics Illustrated. It's a great book. This guy's really cool. I really dig him. Yeah, anyway, if you guys have other recommendations to me, I really kind of think I loved it so much. I took obviously referenced it a lot as a refresher, because the last time, like many of you, I took acoustics was in architecture school. And it really, man, if things had gone differently in life, I think that's an entire field that I would have really enjoyed, is this whole discussion of acoustics. It's this combination of psychological stuff and very practical construction related things. Very neat. Love it.
Awesome. All right. So next question is, how does the double stud compared with a staggered stud wall?
You know what? I don't know specifically. I seem to remember actually, I think I was surprised by looking this up. 2 things. One, I thought the double stud wall would be always better, and that it appears to not really be the case. There are references that show you standard assemblies that give you these ratings. If you just Google this, double stud wall, staggered stud wall, or typical wall assemblies, you can look at the tested ratings. So I will defer to actual people who have done that data, but it is actually sort of surprising sometimes how this stuff works. Stuff that is, and definitely check it, because our intuition is not always right on that. And the degree of performance change often isn't as well. So for example, I thought that double stud walls would be substantially better at improving performance than resilient channels. And that is not always the case. There are some amazing resilient channels that give us really great performance. So if we've got a situation where you don't have a lot of room, but you need a high performance assembly, you don't have room for the double stud, there's a solution you can buy, probably. I mean, which is cool. Now, obviously, there are lots of constraints. You can't do that everywhere.
All right, awesome. Okay, so is there language for specifications that can highlight inspections for air-sealed acoustics, not to be overlooked during site inspections?
No, I mean, yes, but no. How many people read the specifications? And also the types of contractors who are the most egregious at implementing the details are exactly the ones who don't pay attention to the specifications. So yes, I think your specifications should be better. And maybe what I love actually are architects who take the general notes section really seriously and write it in very clear language. So they're not approaching it as sort of a CYA legal thing, like I'm just going to throw a bunch of stuff in here so that it's someone else, if something goes wrong, it's someone else's fault and I can say it's not mine. But if you look at the general notes section and write stuff really, everything, not just acoustics, but particularly water management. Obviously I care about that stuff because I'm a building scientist. I think there is some benefit to doing that there because it's in the general notes. It's easier for people to actually look at that. The thing that I find helps the most is that when you draw the details yourself on the design side, when you draw the details, the act of drawing them makes you think about them. And when you send junior staff, say, on a job site, they have to do a site visit, they have a detail that they can reference because they don't know what they're, I mean, I showed you pictures of me doing blower door tests. That was me 15 years ago. I didn't know what I was looking at. I saved that photo and I was laughing because like I took the photo of I said acoustic awesomeness going on in the photo. I didn't even know what I was taking a picture of when I was, I didn't even
There
know
was somebody in the chat who said that's their new band name, Acoustic Awesomeness.
Acoustic Awesome. Oh my gosh, that is a great band name. Oh, that's fantastic. But anyway, I didn't even know what I was looking at. But having clear details means that you can send more junior staff who have more time to job sites to look at that stuff, and they have a detail and they have something that makes it easier to have a conversation with a contractor because you're like, you know what to look for, and it gives you something to fall back on, which means you're more likely to actually bring it up. It's I don't want to like belittle my own profession by saying this, but I think it helps to acknowledge how difficult it is to put somebody on the spot about the work that they're doing. I am huge. I have been hugely uncomfortable about questioning work in progress on a job site that someone worked hard to do, but you got to do it in these things. And if you're armed with good details on the front end, and you are trained a little bit with what to look for, like look at my photo presentations here. Not good, good. That's a really good starting point.
Great. All right. Sorry if you see me looking down. I've got two monitors going. So
that's good. You're doing. Sorry, I'm exercising some acoustic control right now. We have a new puppy, and she was asleep during the presentation, and she's now deciding she wants to chew my fingers.
Of course. All right. So you showed an example photo of a very good air sealing where the GWB partition hit the deck above. What was different on that project than a typical project that led to the work being done correctly? Did the owner focus on it? Just a good GC?
It was great question. It was well detailed, and we did blower door tests. And the thing with the blower door test is you don't have, I mean, it's great if you test every unit, but you don't have to test every unit to get like 90% of the benefit from it. It works just like window tests, right? When we do water leakage tests on windows, you get a spray rack, the pressure, whatever, you hire some company to come out and go do this. And it costs whatever it costs for your multifamily project, but you're not testing every window. Well, guess what? Every window that gets installed, when people know that it could be tested, they install it kind of different. So that was the acoustic awesomeness photo was that was my first job in multifamily construction, was doing blower door tests and looking for these details. And we cared primarily about our number one goal was. Our secondary goal was acoustic performance. Our number one goal was energy performance. So we were trying to hit passive house standards for each of these units. And so they were very airtight. Now we used as sort of leverage, once you've signed all these contracts, it's very hard to get, sometimes it's very hard to get the performance that you specify, especially if it's something that you're asking people to be more attentive than they usually are. And what we would do, or what we would try to explain what we were doing on the merits to the people we were working with. But if they didn't do it, or if they didn't care about that, we would say, well, this is the fire requirement. Yeah, everybody cares about fire. So you have to do this to comply with fire code, so just do it. So it's sort of funny that air sealing details that provide us with really substantial, like acoustic comfort matters. I know like burning is very bad. It is worse than hearing loud things, but acoustic performance, indoor air quality, these things actually, we should care about these things too. But a lot of times it's like, it's fire requirement, you gotta do it. So that's sort of my personal strategy, but unfortunately it's showing up drawing the details, showing up, asking questions, and speccing the blower door test. Like probably if you're not doing it now and you want to start doing it, probably the best way to start is to, because you're not going to know what to set your threshold at, right? You're not going to know like what should I pick? Should I mandate that it's 3 air changes? Like, how do I know? What I'd recommend is investing in doing a blower door test of each, of several units on something you're already working on and seeing what you hit. Now, this is an investment, but seeing what those numbers actually look like based on your design, your project, your, whatever. And then you'll have a better sense for the next one, what's most reasonable to achieve. The best use of the blower door, I find, is as a QA QC kind of guide. Now this is hard for architects to find the money to include this, but acoustic problems are a big deal. I bet you if you present this to your owner or developer, especially one that you do if you do a lot of projects with, they're going to want to invest. They potentially could want to invest in that too, because these complaints are terrible, and there's not that much you can do apart from relocate people. You can add insulation, whatever, but relocate them and give them money. Who wants to do that? Just do a blower door test. Anyway.
All right, so this next one, is it better to fill the full mid-floor cavity with blown-in insulation versus shallow sound bats? Generally speaking, can you provide best practices detailed for floor and wall assemblies for wood frame buildings incorporating all of the elements discussed?
So interestingly, so I don't know to that fine a level, I don't know the answer, like what the difference in performance is, a complete fill versus partial fill, I don't know. What I do know is that for IIC, for structure-borne sound, insulation in general does very little for us. Now it's inexpensive, and so it makes sense to include it, right? But it's not enough to really solve the problem that we need solved. It's not gonna, you're likely not gonna be able to really achieve much to hit your code mandated IIC rating 50 using insulation. So like using better or more insulation doesn't give you more freedom in picking floor finishes. And it also, as a retrofit strategy, when you've already got a problem, adding insulation for IIC type sound doesn't, it's unlikely to solve the problem. Unless it's a psychological thing where you add insulation and now they think, the occupants, the complainer, think that you've done something, so maybe it helps. But in terms of measure, like a measured difference, unfortunately, insulation is sort of minor.
All right.
So yeah, so with IIC, it's stiffness and mass that are the most helpful, which is, again, this is sort of the whole thesis of my presentation. For airborne sound, we want to air seal. For impact sound, use different stuff. Use gypsum concrete if you're not using this at all, or go, take 2 steps forward, all the way to using a higher performance underlayment like magnesium oxide. It gives you, and this is also like, I didn't know this, if you guys are not, this is, there are lots of people who will probably, I'm making an offer that I don't have to make good on, but I'm sure people would be delighted to send you a sample of this stuff. This is not what I thought it was. Or if,
yes.
This is very, very dense. This is like, you cannot break this. I wasn't using a lame hammer. I was using a real one. Can you see the dent I made? Maybe a little, like you can't even see it.
You can go on our website and request a sample of Exacor, and we will send you a sample. So you are making promises we can keep.
Good. But you're gonna want that. Like anytime you do something, so it is, in a lot of ways, it's easier to enforce something that you're already doing. So the air sealing part is complicated because there's a lot of stuff, there's a lot of detailing. In some ways it's easier, well, I'll just buy something different. But that's not always easier. It's not just buying something different. You have to pay attention to all those other things. How is this going to fit into the existing workflow? And are the other stakeholders going to be on board? So I, as an apartment dweller, I highly support and endorse using things that makes improve acoustic performance. But on the construction side, there is no way I would, if I'm working with a contractor, there's no way I'm going to approve or be excited about a change like this unless I see it. Anyway, it's just reasonable. Part of the job.
All right, we got a few minutes left, so I think we can just one more question. Sorry. So can you address PU spray foams, pour foams, and structural insulated panels? They seem ideally suited for resilient acoustic separation.
No, I don't know about that. I don't know more than you would find out by Googling it. Yes, they are. There are really fantastic combinations of things when we get into the more specialty range. So if your specific focus is, if this is one of your top objectives is acoustic performance, and this is, you're going to market your multifamily buildings on this, you're going to need to do a more rigorous investigation of different approaches. If what your goal is to take what you've got and do a little bit better with basically the same resources you're already using by sort of reallocating your existing resources, that's where the relevance of this presentation is and where my area of expertise is. But into the more specialized stuff, I'm afraid I can't speak intelligently about it.
All right, trying to find, let's see, one more. All right, any benefit with acoustic sealant between subfloor and overlayment?
I don't know how these are tested. Part of the problem with a lot of this is, remember that these are tested values, like they have to be measured, and that it's not like a linear thing. We can't just add it all up. So sort of like R value, we add up the R value of the individual components of a wall, and then we get a total R value, and that's easy. We can't do that with acoustics, with sound. It doesn't behave the same way. So there are just tons and tons and tons of different combinations. So even the ratings that I've talked about, like the ones that I gave you, the sort of estimated STC and IIC ratings, except for the ones in the chart I showed you, those were specifically measured. They were measured by Huber, who was testing their new product. But the other information I gave was sort of estimates, because different people test their proprietary products in different configurations. And when you change a configuration, like you can't just, you have to test the whole thing. You have to test the whole new thing. Sort of like NFPA 285 too with fire stuff. So I don't know the answer to your question. And also your question is a good one and hard to find the answer to, because you have to find somebody who's done that particular test, and that's hard. But yeah, sorry.
All right. So I think that's all we have time for today.